Good evening. Good evening and welcome to another interesting lecture within the module Emerging Fields of Architecture. Today I have the pleasure to introduce Hugh Broughton to you. He has been a lecturer for the module a few times already within the last few years. And Hugh Broughton is here today online. Hugh Broughton founded Hugh Broughton Architects in 1995. Why we have invited him is because in 2005, Hugh's practice won an international competition for the design of the UK's most southerly Antarctic research station, Halle 6. It is a modular elevated base that was completed in 2012, and it is also the world's first fully relocatable polar research facility. Also, I think it is one of the few, if not the only, station that was designed with an architect, but Hugh will tell you more later. Hugh's practice has gone on to win a string of design competitions for remote projects and is now considered one of the world's leading designers of research facilities in the polar regions. His projects include Halle 6 Antarctic Research Station, Juan Carlos 1 Spanish Antarctic Base, the modernization of the Roterra Research Station for the British Antarctic Survey, the Scott Base redevelopment for Antarctica and New Zealand, the Davis Station redevelopment for Australian Antarctic Division, and an atmospheric watch observatory in Greenland for the US National Science Foundation. Also, Hugh has won over 50 international awards for his designs. His work has been published around the world and has been featured in numerous exhibitions and on television and radio. He has lectured worldwide on the work of his practice and regularly sits on award and competition juries. It is a great pleasure today to welcome Hugh Broughton to have a lecture for us at the TU Wien. Thank you very much, Hugh. I'm really looking forward to your lecture.
Thank you, Sandra. It's a real pleasure to be here with everybody. I'm just going to share my screen. So let's go and just get out of that so it doesn't interrupt us. I'm gonna talk to you today about some of my experiences designing buildings in the polar regions, particularly in Antarctica. As Sandra mentioned just now, I've been lucky to work on projects in Antarctica now for around 15 years. And obviously we've learned quite a few lessons during that time. It seems to me that right now, in the midst of what we're told is one of the most important climate conferences in human history, the place of Antarctica in our world could not be more important and in sharper focus, because events which take place in Antarctica have huge implications for everybody all around the world. And in fact, only at the weekend, I was talking with some scientists about a glacier in West Antarctica called the Thwaites Glacier that is being researched by both the UK and the USA, and which is in retreat. If at any point that glacier was to disconnect from the main continent and start to melt in its entirety into the sea, then sea levels around the world would rise by 3.3 meters. That may not affect Vienna, but I can tell you there are plenty of places around the world which would, that extent of sea level rise would be catastrophic. Large sections of London, in fact, would be flooded. Probably lots of the Netherlands, parts of Belgium, France would all be flooded. So it goes to show the significance, I think, of big events thousands of miles away can have on all of our lives. And the research that scientists are carrying out in Antarctica is therefore of absolutely crucial importance in forming the debates that people right now are having about climate change. But let's return to architecture. So these are some of the stations in Antarctica which we've worked on. I'm going to start by telling you about Halle, which is a British station about 900 miles, so about 1,200 kilometers from the South Pole. I'll show you also some slides of Juan Carlos, which is a Spanish base, which we've also designed, and of Rothera, another British base, which we're working on. Currently, we're also working with Antarctica, New Zealand on Scott Base, a major redevelopment of New Zealand's base, and with the Australians on a project at Davis, as well as an aerodrome at Wilkins. So we've had over time a lot of involvement in Antarctica, and in fact, right now we have more involvement in Antarctica than we've ever had in the history of our company. So turning first to Halle at 75 degrees south, it's a very unusual location, even in Antarctica, for a research station, because it's located on what's called a floating ice shelf. That is when the ice has literally flowed off the main continent of Antarctica and is being supported on the sea. At this point, the ice shelf is around 150 meters thick, but it continues to flow out into the sea, a bit like water. Ice also flows, and it's flowing at a speed of around 400 meters per annum. That means that the position of the research station is constantly moving. Now, before we began our design project, this is what Halle 5 looked like. It was made of 3 buildings. The bigger building on the right-hand side was where all the scientists lived. And then the other 2 buildings were science research platforms. One was researching climate and near-Earth snow chemistry, and the other was researching the interaction of the sun with the Earth's outer atmosphere. So significant atmospheric science was conducted even before we started our work in this location. The station climate is extremely cold. In the lowest points of winter, the temperature goes down to around minus 55 degrees Celsius. And even in the summer, the snow never melts. As a result, in the summer, you get very high speed winds, because as the temperature does rise, so cold air from the polar plateau around the South Pole drops down towards the coast where Halle is located. It increases in speed, picks up snow and ice particles, and creates significant snow drift, which will bury everything in the way, including snowmobiles and even whole buildings, unless they're elevated above the snow or ice surface. So it's really cold, and in the summer, very windy. That meant that every year, a crew of 6 steel workers needed to go down to the station in order to straighten all the legs supporting the buildings, which had got moved by the flow of the ice. And then everybody who was visiting or working at the station had to spend around 3 days helping to elevate the building above the ice surface, which they did using small electric screw jacks, which were fixed to the legs to help jack the building up around 1 to 1.5 meters above the rising snow level. So it was a very labor-intensive process. Some of the other factors we had to consider is that in Antarctica, it's dark for at least 3 months of the year. In fact, at Halle, the sun does not rise above the horizon for 105 days. So that introduces another psychological stress for the crew, and also an operational challenge working in 24-hour darkness. And this is what the previous station looked like. It was really quite institutional, not such a friendly interior environment. The building had a central corridor, and then every function had its own room. So there was a dining room, a bar, a room for watching television, And some people found that socially very challenging, especially if they had spent a whole winter at Halle. So they would walk up and down the corridor, almost frightened to open the door into one of these social rooms where they might hear laughter inside, afraid to have to butt in, I guess, on the community enjoying themselves. So quite a lot of psychological stress living in such a cellular space in such a remote location. But there's the benefits that you can go on amazing trips and go and visit some of the neighbors who live maybe between 5 and 10 kilometers away. And here is one of the scientists visiting a colony of emperor penguins who live close to Halle Station. In terms of the logistics, Halle is cut off from the rest of the world for most of the year by around 500 to 600 kilometers of frozen sea ice. But in a small period during the summer, the sea ice retreats to within a few kilometers of the ice shelf itself. And at that point, resupply vessels turn up and can supply all the food and other supplies that are needed to keep the station operational during the year. So here you can see the British resupply vessel arrived next to the sea ice. Everything is unloaded onto the sea ice and then carted across the sea ice up to the edge of the ice shelf, from where it's then dragged to the station. Now, the thing with the sea ice is it's not very thick. It's only around 2 meters of thickness. So the maximum load that you can unload onto the sea ice is only between 9 to 9.5 tons. So when we were considering redesigning the whole station, we couldn't design whole buildings and deliver them prefabricated. We could only design components with a maximum weight of 9 to 9.5 tons. So we had to break the building design down into smaller pieces in order to drag it across the sea ice. So you might think, in the context of freezing weather, high winds, very difficult logistics, and all that darkness, why would anybody want to live in this place? And it's because the scientific research which is conducted here is of truly global significance. And in fact, it was in 1985 that 3 British scientists working at Halle Station first discovered the springtime depletion of ozone, what we call the ozone hole, which led to the Montreal Protocol banning the use of CFCs, which was a really significant piece of environmental legislation. And scientific research and discovery conducted at Halle continues to influence governments and politicians discussing climate change right up to the present day. And in fact, even today, the head of the British Antarctic Survey is addressing the heads of European nations, explaining what's happening in Antarctica and how it is affecting climate change generally. At Halle, however, a significant issue was observed by the British Antarctic Survey, and that is that the ice shelf, which you can see in this zone here, was flowing out to sea, but it was grounded on some rocks in this location and some rocks in this location here. And as a result, stress fractures were occurring in the ice shelf, and eventually those fractures would grow into great crevasses, and everything to the left of the red line would disappear as a giant iceberg. And Halle 5 was on the wrong side of the crack. So it was therefore decided that a new base was urgently needed to be constructed on the right side of the predicted crack line, and that this base should be relocatable, so that the fate of the previous Halles, all disappearing on the ice shelf, should not be repeated. So they held a design competition through a number of stages, and eventually our firm, working with the large engineering company AECOM, won the competition. But before I show you the proposals, let me tell you a little bit about the previous stations. So this is the first research station built at Halle in 1957. It was just a simple timber hut with a pitch roof, sat onto the ice, and then year on year it snowed and the wind blew and the drifting snow amalgamated around the building. So this shot is taken, I guess, around 5 years after the building was first built, and shows the snow having risen up to the eaves of the building. And probably in 2 years more, the whole building was buried. They continued to live in it, even when it was buried, by building timber shafts, which they put ladders into so that they could climb down into the building, until eventually the ice crushed the building and a replacement was constructed. The replacement was a similar timber hut, but then when that also got crushed by the ice, the next generations, Halle's 3 and Halle 4, were built and designed to be buried as tubes in which accommodation was placed, and where the scientists had to climb down ladders to reach the accommodation when buried in the ice. But you only have to imagine how unpleasant that was, with no views, artificial ventilation everywhere, and the smell of all the sewage, the cooking, everything and the generators with their fuel just permeating every aspect of life within the research station. Now, neither of these two buildings lasted for long, Halle 3 for 11 years and Halle 4 for just 9 years. This is the last view that was seen of Halle 3, which was crushed by the ice. And then as the ship was sailing past the edge of the ice shelf, it noticed the remains of Halle 3 being spewed out into the ocean. In terms of other stations around Antarctica, some of them are of quite famous architecture, I suppose. This is the South Pole Station for the USA, which was designed by Buckminster Fuller as a geodesic dome into which accommodation was placed in prefabricated buildings. And this lasted for quite a long time. There's lower snowfall at the South Pole, and also the ice moves a lot less. So the building lasted for much longer, but eventually it too started to develop a lot of stresses and cracks, and was subsequently replaced around 10 to 15 years ago. And this is the newest generation of research stations before Halle was constructed. The top right is the replacement station at the South Pole, which is 2 buildings connected with a link, and which houses around 250 people in the summer and around 50 people in the winter. The bottom right is the Belgian station, which is used only in the summer, but which is zero carbon because it's powered by wind and solar, although it does have generators for those occasions when the renewable sources cannot be relied on. Then there's the German station, bottom left, which is elevated above the ice to allow the wind to blow under, preventing snowdrift occurring next to the building. And then that's also supported on hydraulic legs to help it to climb above the rising snow level. And that's the same approach taken with the French-Italian base, which is made of 2 cylindrical buildings. It's not one for Italy and one for France. It's actually one for science and one for living. But that's also supported on hydraulic legs, which help it to climb above the rising snow level. But for Halle, not only did we need to be able to design a building which would rise above the rising snow level, but we also needed a building which could be relocated if ever the ice shelf was to crack and break off as an iceberg. So our concept was to make the station out of a series of interconnected modules raised up on hydraulic legs and supported on giant skis, which could both act as the foundations, but also as the means of relocating the building further inland if ever there was the risk of the ice shelf carving off as an iceberg. And these are some of the very early sketches that I prepared for the design of the Halle 6. And then as we progressed through the design, we developed these computer-based drawings showing that everything within the station could be accommodated within a standard single-story module. The gap between the underside of the module and the snow is around 4 meters. And these modules would provide space for sleeping, for laboratories, for offices, for communications and the doctor, also as energy centers containing generators fire suppression, water production, sewage treatment, and so on. However, we quickly realized that that would not be the only solution that would work. However, let me just show you here the way that those buildings were intended. The idea was that they would have a steel subframe. That's this element here, which is a three-dimensional space frame, so that you can run the services through that area. That the superstructure would be a steel frame as well. It would all be clad in a super insulated glass fiber cladding and then supported on hydraulic legs with the giant skis at the bottom. And in the science modules, we'd also be able to have roof decks, which would support science experiments and so on. And this is the process of lifting the buildings above the rising snow level each year. So this is what it would look like at the end of winter. So the wind has blown from the right-hand side. It accelerates under the module, picks up snow and causes a big drift at the leeward side. And then that snow has risen there by around 1 to 1.5 meters. So at that point, the legs are lifted up one in turn and snow is pushed underneath each leg. The module is then jacked up using the hydraulics. Snow is filled underneath and the building is left sitting on a flat, icy snow surface, ready for the process to be repeated over the following winter and then be jacked up the following summer. This was our proposal. I mentioned that whilst we realized that most of the functions could be housed within the standard blue modules, we realized that some functions required a bigger module at the heart of the station. And this is our proposal for a 2-story module to provide dining and recreation space, a bar, and then on the upper level space for accessing the internet or watching TV. And early on, this is a drawing we did at the competition stage, we had an idea of having a hydroponics greenhouse at the heart of the station where you could grow fruit and vegetables in nutrient-enriched water, because there's no soil in Antarctica and you can't import biological matter into the Antarctic. But unfortunately, that didn't get built for reasons such as the smell and the concern over having the nutrient-enriched water at the heart of the building. We also had ideas for a climbing wall, but when the Antarctic Survey saw the climbing wall and the bar, they thought there would be some risk of people getting hurt. So the climbing wall disappeared so that the bar could stay. So in terms of the construction, before we actually built the station in Antarctica, we tested everything out in Cape Town in South Africa, where the station was constructed. And the reason it was constructed in Cape Town is because it was cheaper. The people who were building the station there had experience working in Antarctica before, and also Cape Town is a lot closer to Antarctica than Europe. And here you can see that we built both one of the blue modules and the big red module to be able to test the hydraulic legs, ensure the levels of air infiltration into the modules met the design, also just to test that all the panels and so on fitted on to the steel frame. And then when everything had been tested, everything was then loaded onto this ice-strengthened Russian cargo vessel and shipped to Antarctica, where it was unloaded onto the sea ice and then dragged to the site of Halle 6. And here you can see the largest component of the construction, which is the steel space frame substructure of the modules, having been unloaded onto the sea ice and being pulled to the construction site. And this was weighing around 9 tons, so within the capacity of the sea ice. And here you can see the construction site. So the construction took place next to the existing station Halle 5, so the buildings could be used for accommodation for the builders. And it was constructed using kind of factory line techniques. So we had one team doing the steel frame, then another team doing the cladding, and another team doing interior fit out, and then a specialist team devoted just to the big red module. And here are the stages of construction. So this is the space frame just arrived on site, and it's lifted by a crane onto these shipping containers. And then when it's lifted onto the shipping containers, then the permanent hydraulic legs, which are quite heavy, can be installed along with the giant skis. And then from there, the prefabricated flooring is installed on top of the frame to provide a working deck for the subsequent construction. And here is prefabricated building services being installed into the space frame, prefabricated mechanical and electrical equipment being installed onto the floor, and then the steel superstructure being installed. And then this is one of the other modules which had prefabricated bedrooms, bathrooms, and plant rooms, which were loaded onto the floor deck before then the steel frame could be installed and the cladding. And here you see the cladding being installed onto the steel frame. It's made of large panels of glass fiber with the glass already installed. These glass fiber panels, some of them were as big as 10 meters in width and 10 meters in length. This wall panel is around 10 meters in length and 3.5 meters in height. So it allowed for a very quick construction process. And then when the modules were completely weathertight and were also largely fitted out on the interior, they were then moved from the position of Halle 5 to the new position for Halle 6 on their skis, being pulled by bulldozers. And they moved at the speed of around about 10 kilometers per hour, so quite fast. And then when they arrived at the site of Halle 6, they were aligned one to the other, and then they were elevated on the hydraulics and joined together using these flexible connectors like you get between train carriages. And here you can see all the modules connected together. So on the left-hand side, we have two modules here and here, which are science modules. One is for the climate observatory and one is for atmospheric science. Then two energy modules with generators in both, water production in both, sewage treatment and fire suppression. And the reason there's two is if there's some kind of failure in one, you can still rely on the other. And then they're separated by a bridge so that if there's a fire on one side, you can escape to the other until you can be rescued. The big red module is for dining and recreation. And then the next module is the main, what we call command module. It's where the base commander has his office, the doctor is there, the communications room, the servers, and so on. And then there are two modules here and here, which are for sleeping, which accommodate 16 people in the winter and 32 people in the summer. So at the south end, these are the science modules, and the most southerly module has an upper deck with a glazed observatory to allow people to study the climate. And then the next one along has a roof deck on it to allow us to place scientific equipment. And then the next one along is an energy module that has a roof deck on to allow inspection of all the flues for the emissions from the generators and so on. This is inside the observatory. And the guy at the end here, he's taking measurements using a machine called a Dobson spectrophotometer, which is used for measuring ozone. They've been measuring ozone at Halle since 1957, and it was that measurement which led to the discovery of the hole in the ozone layer. And they continue measuring ozone at Halle to this very day. So this is the main social module, and the black glass is actually clear glass, and the white glass is a translucent glass insulated with a material called nanogel that was originally invented by NASA to insulate the end of the space shuttle for when it re-entered the Earth's orbit. And it's really good at, it's very light in weight, it's very good at transmitting light, but it's also highly insulating as a double skin brick wall. And here you can see the effect. So you get the white glass lets lots of light in, the big triangles are actually clear glass looking out onto the ice outside. And this space is really popular in the station because it's so nice and light and people like to congregate in this location. And this is the staircase leading to the upper level. It's lined in Lebanese cedar veneer panels to give off a nice smell. because in Antarctica there's no woods or any natural features really. So it's nice to have the smell of wood around you, and Lebanese cedar is one of the few veneers that gives off that nice smell. Also, to help the British scientists feel at home, there's a nice picture of the Queen on the wall. And then this is the upper level, which has these big domed roof lights, which you can stand in to observe the incredible displays of the Southern Lights, or the Aurora Australis, which are particularly strong at this latitude. And you can stand in there with all the lights off in the room in the middle of winter and admire the Southern Lights without having to go outside. And this is the northern end of the station with the two sleeping modules. Just gives you a little bit of a scale, seeing the person walking past. As I say, it's around 4 meters to the underside of a module and around 10 meters to the top of the module. We work very closely with a color psychologist who helped us choose colors for the station to help people overcome the effects of seasonal affective disorder, which affects people when they live in perpetual darkness. At the heart of each of the modules, the corridor widens out, and there are actually a series of roof lights, windows in the roof, just letting light into the center of the building to reduce the lighting requirement, but also to make a nice light space at the center of each module. We used vacuum drainage for all the toilets and washroom areas because this reduces the amount of water usage per toilet to 1 litre per flush, compared to around 8 litres per flush in a modern standard toilet. So that's significantly reduced water usage on the base from around 120 litres per day at Halle 5 to around 25 to 30 litres per day at Halle 6. And by reducing water, it reduces the amount of energy that needs to be produced to melt the ice to create the water. So it's a very good energy saving device. This is one of the bedrooms where we also work closely with the color psychologist to choose colors which would help promote people's healthy sleeping patterns. Next to each bed, there's also a special alarm clock light, which includes a daylight simulation bulb to help people rise as if there's a false dawn in the middle of the winter darkness. Everyone gets plenty of storage, a desk, a window with pull-down blackout blind. You share a room during the summer and you get a room to yourself in the winter. And here's a view of the station from the northern end at the end of the summer season, when all the snow has been leveled underneath the modules. And this is what it looks like in the depths of winter, when the snow level has risen to one side, the wind has accelerated underneath and is causing a big drift on the left-hand side. You can read a book produced by Part Books all about the station. The station has been used by the British government as a demonstration of innovation. And then it's also appeared on a stamp. It's also appeared on a coin, but unfortunately only a coin which you can spend in the British Antarctic territory. So useful only for buying postcards of Halle or T-shirts with pictures of penguins on. And then my favorite thing is somebody who really loved the design, who I've never met, but they had the building tattooed onto their arm, which I think for an architect is the ultimate show of respect. The best thing for our company, however, has been the opportunity to work subsequently on a series of other Antarctic stations, the first of which was Juan Carlos for Spain on Livingston Island. Livingston Island is a stunningly beautiful place off the Antarctic Peninsula, used by the Spanish during a prolonged summer season from October through to March. On arrival at the start of the summer season, the Spanish often encounter around 3 meters of snowfall on the site. And then during the the summer season, the snow all melts. So the design needed to take account of that. There's also a lot of wildlife round and about the station. You get dangerous leopard seals, big colonies of elephant seals, large colonies of penguins, gentoo penguins, Adelie penguins, and so on. And also quite a lot of rare mosses. There are very few plants in the Antarctic, and Livingston Island is one of the few places where plants do grow. So they need to be very carefully protected. So a very fragile ecology, which needs very significant respect. There are also neighbors. So this is a small Bulgarian base, which is next to Juan Carlos, which I was very lucky to visit, and also be treated to some glasses of homebrew raki by the scientists who lived in the Bulgarian station. So at Juan Carlos, the base would not be moved. It would just sit in one location. Also, the wind blows only in one direction. So we were able to experiment with a different shape of building, albeit also made of rings or modules which could be simply fixed together. And this was the design at concept stage, which was for all the accommodation to be on the first floor level. So when the Spanish arrive and the snow has risen to around the level of the cursor at the moment, they could just go up the ladder and go in through the first floor. And then as the snow melts, they could then enter through this ground floor level, which is where most of the plant and the locker rooms and storage and so on is located. The buildings are just lifted above the ground to protect the lichens and mosses, and also to allow meltwater to flow underneath. And then they have glazed elevations to allow people to enjoy the spectacular views of Livingston Island. The main accommodation is arranged as a kind of three-winged star, and then there's a separate building for science, again, so that if there's a fire, people have somewhere to escape to, which is a really important design feature for Antarctic bases. In terms of delivery, it's really challenging delivering to Livingston Island. There's no port, there's no sea ice to bring a big ship next to. So the ship generally will have to moor offshore, and then we looked at options like delivering by helicopter, as was used at Marion Island by the South Africans in the sub-Antarctic in the top picture here, or delivering by a small cargo barge, as you see used by the British in a place called Bird Island in the sub-Antarctic. And in the end, we opted for this simpler bottom solution. And here you can see some of the cladding panels being delivered. These are the precast concrete foundations on which the buildings would subsequently sit. And here you can see some of the cladding being installed onto one of the utilities buildings containing the generators. And here's the station nearing completion. It's now been fully occupied by the Spanish, and it had its first operational season in 2019. Moving on from Juan Carlos, we've recently been working at this other British site, which is the station at Rothera, which is an absolutely stunningly beautiful location in a place called Adelaide Island, with stunning views of the mountains, but also large colonies of whales and seals can regularly be seen out in the bay just here. The building that we're building at Rothera is actually ground-based because it needs quite a lot of vehicular access, both to the vehicle workshop, but also to science preparation areas for people going out into the field. It's a multi-use building, so it's got vehicle workshops, plant rooms, recreational space, science workspace, science stores, science preparation space, medical facility, and operational offices, including this control tower, which is used to monitor the runway where planes are flying in and out, and also for monitoring marine operations, both for science, but also for logistics. So this project is currently under construction. We've had now 2 seasons of construction, and there are 2 remaining. And it's been a real challenge managing the same level of effort in construction all during the COVID period. Here you can see the size of the building relative to the existing buildings at Rothera, and also the runway, which is used for wheel-based planes that are flying in from South America, either stopping at Rothera or flying on to other locations on the Antarctic inland, whether to other nation stations or facilitating deep field science. This is a model we had made of the building. And you can see there's this big aerofoil detail on the leeward side. So the wind is blowing from this direction, blows over the monopitch roof, and then is captured by this wind deflector and channeled down the facade to clear away drifting snow from the leeward elevation. You can also see that the building includes photovoltaic panels and this controls tower for monitoring the air operations and marine operations. And here's a slice through the building, which sort of demonstrates the multifunctionality: science offices, boot room, workshops, stores, recreational spaces, meeting spaces, and so on. You can also see how the wind deflector works. So the wind blows over the roof, is captured in here, and then blows down the elevation of the building to clear away snow from this facade. The largest project, which we're currently designing shortly to go into construction, is at this amazing place called Scott Base on Ross Island in Antarctica. It sits in the shadow of Mount Erebus, just here, which is one of the few active volcanoes in Antarctica. The station was developed in 1957 and then redeveloped in the 1980s when all these green buildings were constructed. It sits very close to the American station McMurdo. It's just about 4 kilometers away. McMurdo is the largest research station in Antarctica, which in the summer has a population of around 1,000 people. And to many people, it sort of resembles an Alaskan mining town. It's also about to undergo a significant redevelopment where the 100 different buildings of McMurdo will be rationalized down to just 6. Other structures which sit close to Scott Base include some of the really historic huts of the early explorers. This is the hut of Captain Scott from his 1901 to 1904 discovery expedition. He bought a prefabricated building in Australia that was designed for the outback. Hence, it's got this sort of shaded veranda all the way around the edge. It also had virtually no insulation in the walls, and so was so cold to live in that, in fact, the crew only spent one period inside before decamping back to their ship, which they found to be warmer. It's so cold inside that food that they left there over 100 years ago has been perfectly preserved ever since. And it's a really atmospheric place to visit. In terms of Scott Base's history, it was constructed in 1957 as a series of interconnected buildings. And you can see here them all connected with a central circulation corridor. And that concept of interconnection has remained at Scott Base ever since. However, there were a series of problems which were identified, which meant continuing operating from the existing buildings became increasingly difficult. There are multiple different levels because the site is sloping, making it really difficult to move supplies from one area to another. Many of the services are in very, very constrained and tight spaces, making them hard to maintain. A lot of the equipment is very old. The water treatment plant, for example, is nearly 40 years old. Fire safety is compromised in numerous locations. And in fact, this is typical where you have to open the door and then swing it down onto this ladder to escape out of the building. Because of the arrangement of the buildings, snow drifting occurs between the buildings. The snow never melts in the summer. It freezes up against the facade and causes damage, and sometimes snow drifts between roofs and people have to climb up on the roofs to get rid of the snow, which is obviously very dangerous. So we started the process of coming up with designs for the new base. We actually went through a series of different concepts and came up with this concept of interconnected buildings arranged stepping down the hillside, stepping and arranged off a link. And here you can see the eventual solution that was adopted: a building for accommodation, a building for science, and a buildings for workshops and central stores, all connected by linkway. And the buildings elevated above the ground, so the wind would blow under and prevent snow drift, and with a monopitch roof oriented into the strong wind, so the wind would then just blow over the top. And here you can see the cross section of the buildings as they step down the hillside, with the lower level of the upper building connecting to the upper level of the middle building, and then the lower level of the middle building connecting to the upper level of the lower building. And that meant that you could have stores in this bottom building, and they can be taken on the same level through to the area where people are getting expeditions ready. And here's a cross section just through the accommodation building. It's a steel frame with a castellated steel beams at first floor level so that services can pass through, and then all wrapped in a well-insulated envelope made of metal composite panels with a polyisocyanates foam insulation. We proved the shape of the buildings by carrying out snow modeling in a laboratory in Canada, run by a company called RWDI. So you make models of the building, then you drop the models into a tank of water, then you introduce a current into the water, and then drop fine sand particles into the water. And as that sand flows over the buildings, it drops out like drifting snow. And we benchmarked it by, first of all, doing the existing station to make sure that the sand was drifting in the same way that we knew snow drifted around the existing building. And when we were happy with that, we put the proposals in, and we were able to change the length of buildings, change the offsets of the buildings, look at the effects of different locations for ramps and so on. So it was a really iterative process that really helped to drive the design forward. So this is the existing base, and here you can see the proposal with the upper building for accommodation, the middle building for getting ready your science expeditions for going into the field, but also to provide laboratories, workspace for scientists and workspace for operators. And then the bottom building, which has got workshops and central stores and cargo facilities. And then there are areas for putting cargo, helicopter landing pads. There's the historic building from the original 1957 construction, which has been retained and conserved. And here you can see it in the context of Pram Point on Ross Island. The American base is here. This road comes past Scott Base and then leads out onto the Ross Ice Shelf, out to two ski runways, one for planes flying to the South Pole, one for planes returning to New Zealand. There's also a wind farm up on the hill here. The wind farm provides energy both for the American base and for the New Zealand base, and will be, in fact, replaced as part of our project. One of the really interesting things that we've done within the project is engaged on quite a number of occasions with the Maori community in New Zealand, so that there can be a cultural overlay to the project. We talked about issues which are crucial in the design of buildings in Maori culture, and applied many of those principles to the design of the new base. Also talked about the history of Antarctic expeditionary endeavour, that is a key part of New Zealand's history, and how we could reflect that in the design. We drew heavily upon the lessons of Sir Edmund Hillary's historic hut, which had just been conserved with its original colours, and looked at how those colour patterns could even be applied within the new building. Here you can see those principles of his respect for heritage applied to the entrance hall. So there's exhibits of historic artifacts from New Zealand's exploration in Antarctica, information about the base, but also information about science, which is currently ongoing. So it reflects a strong Maori concept of what's called one foot in the past, one eye on the future. This is the briefing room, which has really good views out to Mount Erebus. This is a double height space at the center of the main living building, and some of the short-term bedrooms look into this space, but it's also a place where you can admire pictures of the winter staff over the years at Scott Base. It also features art by Maori artists at one end. It's a cross section, so that was that double height space D there. Those are short-term rooms for 4 people which look into that double height space, and then single rooms for longer term staff, which look out into the landscape. And then on the lower level, there's food storage and plant rooms. And then the facade is angled to direct the wind underneath the building to prevent snow drifting accruing underneath. And then the angled zone is used for distributing services. It's a single bedroom for long-term members of staff. It's got lots of storage, pin boards, peg boards for putting shelves and so on, blackout blinds, and also towel rails so that people can control temperature. It's a cross section through the main dining room, which has a big window looking out at the volcano, Mount Erebus. Here's the dining room. And this is a library quiet room at the opposite end, which is just important, as well as to having places that people congregate. It's also important to have quiet spaces where people can just sit and read a book and contemplate the natural environment, be with each other, but be quiet at the same time. We've looked very carefully at the palette of materials to reflect the nature of New Zealand, but also to cocoon people against the cold landscape outside. Then this is one of the bridge links connecting the buildings together. And then as you come into the middle module, that provides space for scientists to work on the upper level, meeting space, training space, and then on the lower level are all the areas where they can prepare to go out into the field on expeditions. So this is the collaborative workspace. And this is the area for people to get their expeditions together before they go out into the field. And then, so that was the middle building. And then the bottom building here is for workshops and stores. And here you can see a view of the main vehicle workshop. So as you can, I hope, begin to appreciate, these stations have a real diverse mix of spaces within, from bedrooms and libraries and dining spaces through to offices, laboratories, and then at the more industrial end, these heavy workshops for large polar capable vehicles like piston bullies and so on. The main body of the buildings will be clad in metal composite panels with polyisocyanates cladding, and then the ends will be finished with glass fiber details to create curved corners to minimize wind load, and also the bridge links as well will also be made in glass fiber. And then all the windows will be triple glazed. As I mentioned, the wind farm provides power both to the American base and to the New Zealand base. Currently, there are 3 turbines providing 1 megawatt of power. That's going to be doubled with the redevelopment of the wind farm to provide 2 megawatts of power, which means that when completed, 25% of the fuel consumption of McMurdo and Scott Base will be offset by wind power. There's also going to be photovoltaic panels to help boost the power load by a small amount, but still worthwhile. Other ways in which energy will be saved is by using vacuum drainage like we did at Halle to reduce water usage, also using mist suppression for the fire sprinkler system, which needs much less water to douse a fire. It sort of starves it of oxygen rather than putting it out by drenching it. There'll be a bioreactor for sewage treatment, and all in all the measures will help achieve what's called 5 stars in a special Green Star accreditation, so making it one of the greener buildings ever built in the Antarctic. In terms of delivery, we're going for a quite innovative approach. So the buildings will actually be built in New Zealand at a port in New Zealand. They'll then be loaded onto a large flatbed roll-on, roll-off ship and then sailed across the Southern Ocean. And then on arrival in Antarctica, they'll be wheeled off the ship using these self-propelled motorized transporters, which will guide the portions of the building into location where they can be joined together. And the whole base is divided up into just 8 big chunks, fully fitted out inside with all the cladding on. And there's a view of the completed station, so accommodation, science and operations, workshops, and stores with roof decks for communications and another roof deck for scientific equipment. The redeveloped wind farm on the horizon here. And last project I was going to show you was one that we started in lockdown. I've actually never met the client. We've developed the whole design on Zoom and Teams, and it's for the redevelopment of Davis Station, which is an Australian station. Davis Station, just like Halle and Scott Base, was established in 1957. The reason why so many of these bases were established in 1957 is it was classed as an international geophysical year. So it was kind of in celebration of polar science. The station has developed in a rather piecemeal fashion over time and now has around 30 to 40 buildings. And our master plan that we've developed for Australia will help to reduce those down to create a more efficient footprint so that much of the land taken up by existing buildings can be returned to nature. The principles that we're applying to the master plan are ones by now I'm sure you'll recognize from the other stations. Principles of flexibility to allow growth and change during the life of the station. Designing for simple maintenance so all the services can be easily reached. Elevating the buildings so the wind blows under to reduce snow management. Maximizing use of renewable energy and therefore enhancing the sustainability of the station. Designing for the well-being of the crew using both natural materials and good artificial lighting and exploitation of views and daylighting, and then creating excellent facilities to support science for the next 50 years. And here you can see the concept of elevated buildings for living, for sleeping, for science and technology, also for utilities, and then ground-based buildings for workshops, stores, generating power. This is the proposed inside of the dining space with views out onto the landscape, and then potentially, here we are trying again to get the hydroponics into this part of the building, but also good lighting just to make a really comfortable but also inspiring space for the scientists. So the station can be changed from this through to this. And that, I think, is pretty much my last slide, showing what the Australian base will look like during winter in the Vestfold Hills in East Antarctica. So that is the end of the talk. So if anybody wants to ask any questions, I can see that there's quite a few questions in the chat. So maybe I'll just go through some of the questions here and see if I can answer some of those. So first question is, what fluid is used?
Can I interrupt you just
Sure.
a second? I think it would be nice if choose a question, but let the student ask the question.
Oh, sure. Yeah. Okay. Well, the first question actually comes from Philip Halwax. So Philip, please do ask your question.
Yeah, first of all, thanks for the talk. And I'm quite curious what fluid is used for the hydraulic legs, because because of the harsh temperatures.
Yes, quite right. So for the hydraulic legs, it's actually a sort of oil-based solution. It's a hydraulic fluid, which is actually oil-based, which is used to drive the hydraulics. And in fact, the tank where the fluid is stored is actually inside the building, and all of the hydraulic rams, the legs are actually encased in insulated cladding, and then they have what's called heat tracing that runs round the leg, so it keeps the leg warm, so it makes sure that the fluid is always operational.
All right, thank you.
Cool. Next question comes from Paul Papaleka. Paul?
It's a quite interesting design. It reminded me a lot of Star Wars. And my question is, like, how much do the final modules weigh? And is it possible to move them with the equipment that is on site, or do they have to be moved with bulldozers that have to be brought in?
Great question. So so much work went into both calculating the weight of the modules, but also ensuring that the weight would not exceed the power of the equipment which is retained on the site. So the heaviest building is the big red building that actually weighs around 200 tons. And then each of the blue modules weighs between, it depends which one you're looking at, but between sort of 65 to 90 tons. And they can all be used using tracked vehicles, which are retained on the site to support deep field expeditions. So no plant needs to be brought in. And that was a key design requirement.
Okay, thank you.
Cool. Next question comes from Tobias Schiffman.
Hello, thanks for the talk. I was wondering if the foundational skis are somehow anchored in the ice beneath, because I was wondering if there are high wind loads, how is it possible that this doesn't move at all?
Great, yeah, great. Another great question. So when we originally designed the station, we actually designed a hole in each of the skis so that you could ram a steel plate through the ski to help lodge it in the ice so that they wouldn't move when there was excessive wind speed. And that was tried, and it was quite a labor-intensive process. So then the next year, they just didn't bother, and they just left the modules sitting on the ice. And the skis froze really solidly to the ice, and the buildings didn't move. So they never needed to secure them to the ice again. And even though the ski freezes really solidly to the ice, all you have to do is hit it once really hard, and the friction grip between the ice and the steel breaks, and then you can move the modules at that point. So we designed to lock them into the ice, but found it wasn't necessary.
So the nature did the foundation afterwards.
Yeah, exactly. Yeah.
Okay, thank you.
Cool. Next question comes from Franziska Auer.
Yes, concerning the Halle station, why did you decide for this very linear arrangement? Because I'm wondering, you've shown it on another station in the presentation, but why did you go initially for this very linear arrangement? You could also surrounded the red station with the little blue ones, like
Sure.
in centralized arrangement. Is there a special reason for it, or?
Yes, there is. Yeah. So yeah, great question. In fact, when we first did the design, we had the red module in the middle, and then we had four lots of 2 blue modules, sort of radiating out. So it was like a starfish. And then we took it to see the snow modeling company in Canada, and they told us it would be a disaster because the wind always blows from one direction, and therefore the wind would accelerate under the first blue modules and then would bury the second blue modules. And they told us you have to put the buildings in a straight line so that the wind will blow towards the modules, it'll accelerate underneath, and then it'll create the snowdrift on the other side, and therefore it won't affect the buildings. So they're in a straight line to prevent them being buried by snowdrift. But that wasn't what we first wanted to do. But, I guess we learned in that way that the best thing was to put in that location, put them in a straight line.
Okay, very interesting. Thank
Cool.
you.
Next question comes from Sebastian Lengauer.
Yes, hello. Thank you for the presentation. I wanted to ask about the designing process because I found the snow modeling process very interesting, and I wanted to ask if you came up with or had to invent other designing processes or how to test the design for the extreme conditions.
Yeah. Your question on here says that they look a lot, the final modules look a lot like the sketches, and it is true. So we must have been thinking about some of the right things right at the very beginning. But of course, one of the things that I find increasingly with architecture is that, we're generally, as architects, we often have a good, strong sense of what is the right solution very early on in a project. But of course, we then have to spend a lot of time proving that concept, testing that concept, and demonstrating its validity. And at Halle, we certainly did that. So not only did we do the snow modeling, but we also had models of the building made, which we put into a wind tunnel to see how they would perform under very high winds. And we even had models made, which we placed onto the snow at Halle to see how they would behave with the actual snow and wind speeds that you get at the station. We also did computer-based modeling to show how air would move around. And then, of course, we made the test modules. We also did lots of testing on other pieces of equipment that go in the buildings to make sure that they would work. So we did do a lot of testing to prove that a concept, which actually was developed quite quickly, would work. So yeah, it's ironic that, you know, the design process is almost a bit like the tip of an iceberg. You come up with the concept as the tip, but then it's all the stuff underneath which goes to proving that process. But nice question, thank you. Next question is to Madja Sazbio. Maybe I didn't say the name right, sorry. Madja, are you there?
Maya?
Ah, Maya, sorry.
Maya Sabo. Okay, let's
Shall we move on?
move to the next, yes?
Yeah, the next one is from Rhoda Hanif.
Hello, thank you for the presentation. I actually have two questions. The first one is if there's any particular reason for this bold color choice on your exterior glass fiber cladding. And the second is the degree of inclination on both the roof and the one below. So the roof is, I saw on your Davis project to that on the previous one, you have an inclination on the roof that you don't have over here. And there's a degree of inclination, which is sort of cantilevered if it is supported. So two questions, sorry.
Okay, so in terms of the color, I guess there's sort of two aspects to color. So the first is that in bad weather, it's important that the buildings are highly visible, so that if people, you know, stray away from the buildings, they can still see them very clearly. Most of the photos I've shown you have been in really good weather, but it's not like that all the time. And often, you know, as I'm sure from Austria, you will all know, you get total whiteout and it's really hard to see. So therefore, the bold colors are good for that wayfinding. I think there's a sort of geopolitical aspect as well, which is important, that these buildings represent the scientific endeavors of their countries. They're paid for by governments. And so the bold colors, you know, sort of help with their identity. And people like to exploit that identity to demonstrate the scientific activity that they're taking place in Antarctica. So there's a kind of a functional side and an identity side. Now, in terms of the building form, we always try to have some roof pitch or inclination, because even if the snow doesn't sit on the roof, you still get frost on the roof. And then in the summer, when the sun shines, it does actually melt. So you want the water to shed off the building, otherwise it will freeze in the joints and damage them. And then we have sharper angles on the underside of the buildings so that we can channel the wind underneath to stop snow drifting. So the sort of form of the buildings is very much driven by the climate. You know, a few people are making this comment about them looking a bit space age, and I think that comes from that shape that responds to climate, but also probably comes from elevating the buildings above the ground, so it sort of almost looks like they're hovering.
Thank you.
Cool. Next question is from Rom Svist.
Yeah, hello.
Hi there.
Yeah, so thanks for your presentation. So, and you told about the living in Antarctica. And my questions are excursions to this lands, and if it's possible to adapt Antarctica to a place of rest to make it a tourist magnet, and how expensive and possible is it?
Yeah, I mean, you can make trips to Antarctica. There are quite a few companies that do big ship cruises to the peninsula, and the passengers get taken in small boats to go and see the wildlife. Then there are other really expensive trips that take you actually to the continent and even allow you to do, walk the final few kilometers to the South Pole. But if you go on a 10-day trip to Antarctica and do the final 2 or 3 kilometers to the South Pole, it'll probably cost you, that week's worth of holiday will probably cost you between, I would say, sort of around $60,000 to $75,000 for the week. So it's not a holiday for many people. I guess there's Antarctica is protected by a special treaty, which has a number of environmental protocols attached to it. The idea of the continent, and the treaty was signed by around 60 nations. The idea is that Antarctica should be protected for science, and that its natural resources should never be exploited. And I guess there is an issue, therefore, with the potential for tourism to cause damage. So restrictions on tourism are quite heavily managed by all the signatories to the treaty to try to minimize the environmental impact. And in fact, when we're looking at future designs of stations, we're always looking at ways to maximize automation and research that can be carried out by drone or submarine to limit the impact on wildlife and limit impact on the environment generally.
Mm-hmm. Okay.
Yeah. Cool. So
Thanks.
Next question comes from Flora Munzer.
Hello, thank you for your talk. It was really interesting. So I was wondering how you deal with the energy production during the winter season. I mean, there's like a summer season there and winter season where it's very low light or like almost no light. And how do you, do you have other energy production options? Or?
Sure, yeah.
Yeah.
Great. And you're right, because it's dark for over 3 months of the year, longer in some locations, then it's not very good for photovoltaic energy. So photovoltaics is good in the summer. At the Spanish base, they do actually have a building which is has quite a significant number of batteries inside for storing the solar energy to then use to power some small science experiments. But to power the whole base of solar energy would be impossible, especially during the winter. So, for example, at the New Zealand base, that's then supported by wind energy. In fact, the wind energy is the main source of energy. But to be honest, at most bases, they also have petrol-based generators. And because the battery storage technology just isn't good enough to store the passive generated energy all through the winter. But I'm sure that that is one of the things that is going to change over the next 10 to 20 years, that battery technology will improve hundreds of times by comparison to today, and we will be able to store the energy that we generate through the wind and the sun, so that we can finally do away with petrol-based energy. But nonetheless, at the moment, that's how that is managed.
All right, thank you.
Cool. Next question comes from Yizu Han.
Yes, hello. And my question is it possible for these ice layers to break, or the other movement to make an uneven ice surface? And in that cases, what measures can be taken to ensure these cabins are still safely connected as a whole?
Yeah, well, it kind of depends on the location. So in the first project I showed you, Halle 6, there is constantly the danger of the ice shelf cracking off as icebergs, which is why the building is designed as a series of small buildings connected with flexible connectors, so that they can be split apart and then skied individually to a new location and then reconnected. In most of the other cases, the Spanish station, the Australian station, and the New Zealand station, for example, the buildings are built on firm ground, so there's not the risk of them disappearing. But wherever buildings are put on the ice shelf, then they need to be able to be moved. Otherwise, they will have a very short life. So that's why we design them on skis and as smaller buildings that are then connected together.
Okay, thank you.
Cool. So Philip, I think you asked a question already, but you've got another question here around best ways to produce energy.
Yeah, I mean, you kind of already have given an answer to that, but yeah, I want to know what the best or main way to produce energy is, like wind turbines, solar. Or,
it's really interesting as well. It sort of varies between nations, the commitment to sustainable energy. And it's I'm particularly excited that the New Zealand base will have, at least 70% of its power produced by wind, and on some days 97% of energy produced by wind. There are other nations that have invested very little in passive energy generation, and I just hope that there's going to be greater pressure on all countries to invest heavily in sustainable sources of energy in the future, because I think when one country proves that it's possible, it becomes inexcusable for the others that they don't do the same thing. And I really hope all of you as younger architects, as you go into practice, will face up to your clients and pressure them into investigating the sustainability of their projects, the passive measures that can be introduced to improve their performance, and drive down the impacts that construction generally has on the environment. Sorry, that's my little lecture, but I hope everyone's on board with that idea. Next question is from Marcel Hecker.
Yeah, thank you first for the presentation. It's really amazing, these projects. They look like science fiction, but they are not. They are state of the art. You kind of answered my question already when you answered Ron's question. I was wondering, how do you see the future of Antarctica in terms of construction? You said that there was a treaty signed by 60 countries, so that they only build in the for science, basically. But do you think this will hold up, or like who in general is allowed to build?
Yeah, so although there is the Antarctic Treaty, early on the treaty was signed, I think, by just 8 countries, and then other countries have joined the treaty. And it's always amazing to see the increasing interest from countries in developing research stations in Antarctica. And China now, for example, has 4 stations. India has 2 and is thinking of developing a 3rd. Russia is just building a new station. The British are redeveloping theirs. The Australians are redeveloping theirs. The Americans are undergoing significant redevelopment. There's a lot of work going on in Antarctica. And I think, part of that is driven by the need to understand climate change better. Part of it is driven by political ambition to demonstrate scientific prowess. Will there be increases in construction? There shouldn't be, because more and more of the science should be done remotely. More science should be done using autonomous research vessels or drones and that kind of thing. But against although the technology maybe would allow for that, I think the geopolitics probably means that there will be continued periods of construction in Antarctica as people kind of assert their presence. And it's kind of interesting observing that. And as architects, what do? We have to try and at least minimize the impacts of those buildings on the environment. At the moment, all the buildings, it is obligatory that they're constructed for research, and they have to be submitted to consultative meetings of the Antarctic Treaty signatories, essentially to get permission. It's not quite like a local consent, but it's like everybody agreeing, that station needs to be built because it will be doing this amount of science that no one else is doing. Next question comes from Leili Porteret.
Yes, maybe this has already been said, but my question is, what do you do with the old replaced bases, and are the material recycled or reused? And are all the different pieces brought back to the continent, for example, Africa, or yes?
Yeah, so when buildings are decommissioned and replaced, then they are brought back to the nation who constructed them for recycling. I think there is more of a move to repair and reuse buildings when possible, and in some cases, one nation has even sold a base to another nation. So, for example, Britain used to have a base called Faraday that it sold to Ukraine for £1 UK, and which Ukraine now operates as their research station in Antarctica. But the general rule is to remove all the materials for recycling where they came from. We now have Maya, whose internet had broken down. So Maya, do you want to ask your question from earlier?
Yeah, I'm back, sorry. My question was, because you mentioned that you use the ice water as normal water, do you have like the filtration system to reuse it again? Or is it always just melt down a new batch?
So the water is, in some stations, the water is made by melting ice and then goes through a number of special membranes to filter the water so it can be used for drinking. Probably the majority of stations tend to be on the coast because it's easier to resupply them with ship. And then in those cases, the water is made using a process called reverse osmosis, which basically desalinates the water. So it also goes through a number of membranes, and then you get a certain level of purity that you can use for flushing the toilet or for having a shower, and then an enhanced level of purity that you can use for drinking and for cooking. So there are different methods of water production depending on the location. And when we were designing the Spanish station, we actually utilized 3 different methods of water production: melting ice, desalination, and also extraction of fresh water from a lake above the station, which for a short period, the ice melts and creates fresh water there. Cool. And then next question comes from Miriam.
My question was already kind of answered. It was kind of the same like lately. So what happens to the waste?
Sure.
Which is...
Yeah, I could expand my answer a little. So there's like the waste from replacing buildings, but there's also just the general waste. So for example, there's waste, human waste, which has to be dealt with. So each of the stations has a sewage treatment plant. And for example, at Halle or at Scott Base, we had a sewage treatment system, which has what's called a bioreactor, which means that what you get at the end is like a kind of dried sludgy material, which is then incinerated. So it doesn't have to be sent back to the UK or New Zealand. Then you get things like waste from packaging. Some of that is incinerated. The rest of it is packed up and returned to whichever country it came from. And, coming up with efficient ways of dealing with waste reduces fuel consumption, both in transporting it back to the home country, but also in just kind of like moving it around the site. So, for example, when things are being sent out to the Antarctic, they're often unpacked first, put onto a general pallet for transfer to the Antarctic, so that you're not having to ship all the packaging then back to wherever it came from to start with. So considering waste management is a really important part of the design process. And that kind of brings me to a kind of general point about I find one of the interesting things about working in the Antarctic is it's not just an architectural challenge. There's big engineering and environmental challenges which sort of become part of the design process. So you do get to learn a lot about things that in other projects which we work on architecturally, we probably wouldn't learn so much about. And if you don't understand the engineering of an Antarctic research station, it's going to be really hard to apply the architecture. And then I think last question I have here comes from Marikita.
Yes, hello. I would kindly like to ask you, first of all, thanks for the presentation. It was really inspiring. if there were any like unpredicted problems that you faced during the building process. Like I can imagine even in like our building phases, we've deal with problems at the construction sites, and I would be really interested to know if there were any plan changes due to conditions.
Sure. So interestingly, because most of the buildings tend to be prefabricated, by the time they get to be shipped to Antarctica, most of the problems have already occurred. But when, for example, we were building Halle, we had some really big issues with the building envelope. And that nearly meant that we lost the whole construction season. And we had to do lots of changes to the cladding so that it worked properly in the Antarctic environment. It was because it was made in glass fiber, and glass fiber is essentially made of two ingredients. One is the fiber and the other is the glass resin. And there was some of the, and it's quite a handmade process, even though it looks quite space age. And there were some areas of the panels, they were made in South Africa, where the quality control was very poor, and we got way too much resin and not enough fiber. And it's a bit like making concrete without reinforcement. Just the cement will crack if the reinforcement isn't there. And it's the same with glass fiber panels. If the resin is too thick, then it's not getting its strength from the fiber, and we did get cracks. So it was a sort of nightmare scenario, and we had to end up spending a whole extra year, in fact, bringing in a quality control process into the factory in South Africa to make sure that the quality of the panels was good enough. I think that was probably the worst problem that we've had to deal with. On our project in Rothera at the moment, we've had some challenges there in terms of drainage and some damage to some of the flooring while it's being shipped, which again becomes difficult to deal with because you can't just go and get some more panels. You actually have to wait until the next year. So then you have to reorder the way in which the work's done and try and minimize the impact on the project. But the one really good thing about all these projects is that you generally have very, very skillful construction teams and people who are very, very dedicated to the projects. So they're prepared to put in long hours and think of really clever solutions when things go wrong. So, I mean, yeah, I'd say mostly the problems have occurred when we've been building in Europe or in Africa rather than when we've actually been on site in Antarctica.
Wow,
cool.
I see. Thank you very much.
Cool. Well, I think that was the end of the questions, but there's some really awesome questions there. So thank you very much, everybody, for asking those. And it's always nice to be challenged and make sure that we're doing the right thing. And your questions help me just to refocus and make sure that we are. So that's awesome. Thank you.
Thank you very much, Hugh. Can I ask you one more question?
Sure, if it's not too tricky.
What about windows? We have seen a lot of pictures of carefully placed windows in the group areas, social areas, but we have also seen images of spaces where there's no window at all. Yeah,
I think it just depends. The views out are very important because from a social and psychological well-being perspective, I think it's important not only to have daylight, but also to be able to see out into the surrounding environment, because it's very beautiful, but also because it's really important to be able to see the weather and to appreciate the challenges of the environment that you live in. If you can't see that it's blowing a big storm, you don't realize how dangerous it is. But of course, windows, you lose a lot of heat through the window, even if it's triple glazed and filled with gas in the cavity. So we're quite careful in the placement of windows. But having said that, glazing technology is quite sophisticated now. So, for example, in the dining room at Scott Base, we have a really big window for looking out towards Mount Erebus. and not much different from if it was in a ski resort or something like that. And I think that's also one of the things to remember about these projects. Antarctica is a challenging place to build, but I'm sure through all of your work you'll have come across amazing projects built in the Alps that because you come from Austria just probably seem like second nature to you. And we shouldn't imagine that building in Antarctica, it's further away, but the climate challenges are pretty similar to building halfway up Mont Blanc, for example. And in halfway up Mont Blanc, there are some equally spectacular energy efficient buildings which make best use of the views and so on. So I guess we take a sort of similar approach.
Thank you very much. We have one more question from Sebastian, please.
Yeah, I asked the same question about the moon station. Is it possible in Antarctica to store food outside somehow, or do you have fridges in the?
It's mad, isn't it? We have fridges, and the reason that we have to have fridges is because food is generally frozen at around -20 to -25 degrees Celsius, and sometimes the temperatures are going down to -50. And then on other occasions, the containers heat up and they might go above freezing. So then the frozen fruit defrosts. However, in most of the new bases, we try to keep the food stored inside the buildings. So they're within the kind of thermal envelope. The good thing about fridges and freezers is that they do require much less energy because they're not having to cool the external air. Sometimes they're even having to warm the external air. We don't tend to keep the food out on just sitting outdoors, on just sitting on a pallet because it would get frost damaged and so on. So I guess the short answer, it has to be stored inside, and the second answer is we actually even have to use fridges.
Thank you.
Cool.
Thank you very much. Thank you very much, Hugh. Thank you very much, all the students, for these lot of questions to you. It's great to have some interactivity, and I hope we see each other soon here at the TU Wien.
I would love that very much. I've so enjoyed it the last few times, and sure it'll be even better the next time.
Yes, I'm very looking forward to it.
Brilliant.
Hugh, maybe do you have a question to the students before we finish?
I guess my only question is, as architects, I guess you must all be looking at the environment and the climate, and how do you feel what future do you think is in store for you as architects, and what role do you think you can all play in helping to limit impacts on climate? It's such a big issue at the moment. It's going to be such a key driver in your careers. What are your sort of, anybody have some specific thoughts they'd like to give around that? Maybe too difficult a question.
No, it's a very good question, especially for the module, because we have been talking about that. And I know that we have a lot of interesting possible answers. Please don't be shy. Just talk.
Yeah, I could, sorry. Did somebody else want to?
Go on.
I think it will be important to implement thoughts about climate change in every step of the designing process. I think, and in almost any project, I guess. But that's already happening, I think. But
yeah,
well, I don't know.
Yeah, not on the level that we did have some projects about like the rise of the water level and how we're going to react to that, because this is like it is how the climate change makes its appearance, which is not what we've used to see, but this is something new, and suddenly or like gradually, many places will be halfway like floated. So I think maybe we architects need to get in that way as well and start talking about how are we going to solve the problem. For example, Venice is like even now faces such problems with the floods, and yeah, maybe we should rethink the way we build, the way we do foundations, how close to the water we build, and what would be the future to that.
I think it will become, I think that, you know, in all your careers, it will be the first question that people ask, whereas up until now in my career, it hasn't been. It started off not being a question, and then it's emerged into being a question, but not the first question. But I think, you know, no longer will, oh, how beautiful does that building look? That won't be the first question any longer. It will be, how does that building affect its environment? That will be the first question that people ask. And people will no longer say, how much does that building cost? They will ask, how much carbon does that building emit? And that should be the question that people are asking before they care how many dollars, because it may cost hardly any dollars, but if its impact on the environment is significant, then I guess none of us want it. So I think these are probably the first questions that increasingly people will be asking.
Yep, that should be right.
I think one important point is the how we choose the materials we build with. I think it should be well balanced between state-of-the-art materials and, if possible, regional materials, and how to combine them.
Yeah, I think it's true, and we should be kind of utilizing technology, not just for the sake of it, but also using technology to reduce impacts.
I feel like it's really important that we think more circular, in like a circular economy, also like where do the materials go, reuse after maybe the building is recycled, and also every material flow connected to the building. And what you said, that it will be normal that people ask for the carbon emission. It's not right now the case, and I hope it will be normal. And I think for that to really be normal, we need to create positive visions of nice projects that are portraying these kind of ideas, like you did with your first station. It feels like this idea with the first station your office did was so amazing that now you do these many stations, right? I mean, that's kind of what it feels like to me when I saw your presentation.
Sure. Yeah. I mean, one of the things we were hearing about recently as well, in terms of the reuse of materials, is an idea of almost developing a passport for existing materials, so that you have information about their qualities and technical performance to help them to be reused. You know, you can go into a shop nowadays and you can buy a secondhand shirt or a secondhand pair of pants, and you know, you can know it's been well looked after and well cleaned, and you can inspect it and you can choose it for yourself. And you know, for building materials, it's not just okay to bring them back and then recycle them. Why can't we just actually reuse them? So I think I absolutely agree. I think the idea of the circular economy is still quite kind of new, but especially in construction. But it's the circular economy in terms of materials and the reuse of existing buildings has to be one of the best ways to minimize impact, and you know, will become more and more and more important. It's not okay to just knock down a building and build a new one. Every time we should be asking, what's wrong with the old one?
Yeah, but unfortunately it's sometimes cheaper, and that's,
yeah, I know,
that seems to be sometimes the reason to do this.
Yeah. Maybe there's a big role as well for all the city municipalities to put bigger pressure on people to declare the emissions related to their project. So, you know, when you do an application to build a building, you actually have to say what your impact on the environment is, and there should be limits that would be unacceptable. I mean, I look in the City of London, where we get the Architects Journal in our office, and a few months ago, there was like a 30-story all-glass office building, which was featured. And no one will work in that building because nobody wants to work in that environment in COVID. And it's the level of air infiltration in the building was really poor. It was like 7 or 8 cubic meters per square meter, which is really poor. And the amount of energy the building was using was awful. And I was like, well, first of all, I didn't think the magazine should be promoting this building because it's really bad practice, no matter how nice it looks. It doesn't look nice if it's polluting the environment. That immediately makes it ugly, in my opinion. And secondly, I think that the authorities in London should have been asking questions about the performance of that building before they gave it consent to be constructed. And I think we'll see big changes like that coming forward. I hope so anyway.
We hope so too.
Good. Cool. Brilliant. Well, thanks, Sandra. It's been great. I've really enjoyed the session.
Thank you, Hugh. It was good to see you, good to hear you, and good to get your input.
Thank you. All right. Have a great time, everybody, and stay safe.
Have a good evening, all of you.
Take care. Bye-bye.
Bye.
Thank you very much.